So we're going to have a look at another question from the topic of ordinary differential equations. Ordinary differential equations. So this time we're going to have a look at a third order ordinary differential equation. So we are told to solve the following. So the direction is just solve. Y prime 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 minus y double prime minus y prime plus y is equal to 0. We are told y of 0 is 2. We are told y prime of 0 is 1. And we are told y double prime of 0 is 4. Alright, so I'm going to solve this. So if we have y triple prime minus y double prime minus y prime plus y equals 0, we can work out the characteristic polynomial. So this is going to be r cubed minus r squared minus r plus 1 equals 0. Now this is a cubic. We have to try and factorize this to find out what the roots are going to be, and then the roots are going to give us information about the solution to this differential equation. So the first thing we want to do here is we want to see if there's any factorizations which can go on here. Well, one thing we could do, we could factor minus r squared out the front of the first two terms, and we would get the r squared, the r cubed would become minus r, and the r squared would become plus 1. And then the second term, we can factor 1 out of it. We have plus 1 times minus r plus 1 is equal to 0. We can factor minus r plus 1 out of both of these. So this will give us minus r plus 1 times minus r squared plus 1 is equal to 0. So this tells us r is one solution, and then we have two extra solutions which are solved for r is the square root, the positive negative square root of 1. So that is r is 1, and then r is minus 1. So we've been told r is 1, we've been told r is also minus 1, and 1 is a repeated root. So that's something we want to take into consideration when we are solving our solutions, when we're finding solutions to this DE. We know that if we have two distinct roots, then the solutions will take the form y of x is equal to a times e to the r1x plus b times e to the r2x. And if we have repeated solutions, they will take the form y of x is equal to a e to the r1x plus bx e to the r1x. So collectively, we should have three solutions. We should have an a e to the r1x, a b e to the r2x, and a bx e to the r1x. So this suggests for us that our general solution will be y of x equals some constant. Now the a's, we've got to be careful with these constants. They're going to be three different coefficients in front of these. So a e to the r1x plus b e to the r2x plus cx e to the r2x. This is assuming the r2 is the repeated root. So we have r is 1, r is 1, r is minus 1. This means r1 is minus 1 and r2 is 1. So our general solution is y of x is equal to a e to the minus x plus b e to the x plus cx e to the x. And this is our general solution. So this is our set of solutions to this third order differential equation. This is a third order DE now because it's the highest derivative is a third derivative. So now we want to take the derivative of this and then the second derivative of that. We want to use the three pieces of information that we've been given here, and we want to find the values for a, b, and c. So this is our function. So our derivative, y prime of x, well, the derivative of a times e to the minus x is minus a e to the minus x. Derivative of b e to the x is just b e to the x. Cx e to the x is a product rule. So this is u, this is v, u is cx, u prime is c, v is e to the x, v prime is e to the x. So this last term breaks into u prime times v, which is c e to the x, plus u times v prime, which is cx e to the x. So this is our first derivative. Now we need to take a second derivative. So our second derivative, y double prime of x, minus a e to the minus x becomes a e to the minus x. We have b e to the x and c e to the x. They just stay as they are. b e to the x plus c e to the x. And then we have cx e to the x. Well, this becomes c e to the x plus cx e to the x because we just differentiated it here. It became these two terms. So we now have 2c e to the x's plus cx e to the x. So we have a y, we have a y prime, we have a y double prime. Now we can plug the initial conditions into this to help us solve a, b, and c. So I'm going to change color here. I'm going to say the function y, we know y evaluated at 0 is 2. So 2 is equal to a times e to the minus 0 plus b times e to the 0 plus c times 0 times e to the 0. Well, this term just goes away. This becomes 1, this becomes 1. So the base function tells us that 2 is equal to a plus b. So we have a relationship between a and b. The first derivative, y prime of 0 is equal to 1. So this means 1 is equal to minus a times e to the minus 0 plus b times e to the 0 plus c times e to the 0 plus c times 0 times e to the 0. Well, the c times 0 times e to the 0 term is 0. E to the 0 is 1, e to the 0 is 1, e to the minus 0 is 1. So this yields for us the result that 1 is equal to minus a plus b plus c. So this is a second equation. This was our first one. This was our second one. Now we need to evaluate the second derivative. So y double prime tells us that the second derivative when evaluated at 0 is 4. So we have 4 is equal to a times e to the minus 0 plus b e to the 0 plus 2c e to the 0 plus c times 0 times e to the 0. Again, the term with the 0 cancels. E to the 0 is 1, e to the 0 is 1, e to the minus 0 is 1. This gives us 4 is equal to a plus b plus 2c. And this is our third equation containing a, b, and c. Now we can solve these in a variety of different ways. I'm going to use a matrix. So I'm going to put this into a nice little matrix. I'm going to say first column is A, second is B, third is C, and then the fourth is the equals. So we have A plus B, no C, is equal to 2. The second equation, we have minus A plus B plus C is equal to 1. Third equation, we have A plus B plus 2c is equal to 4. Now I need to reduce this so that we have only ones along this diagonal. This is a Gauss-Jordan matrix reduction. Gauss from one side, Jordan from the other side. They both discovered it at the same time. So we will first, the first thing that we're going to do in order to solve this is we are going to add row 1 to row 2. So row 2 will become row 2 plus row 1. Going to subtract row 1 from row 3. So row 3 will become row 3 minus row 1. So this will give us a new matrix, 1, 1, 0. Second row, we are we're adding the first row. So minus 1 plus 1 is 0, 1 plus 1 is 2, 1 plus 0 is 1, 1 plus 2 is 3. And then the third row, we're going to minus the first row. 1 minus 1 is 0, 1 minus 1 is 0, 2 minus 0 is 2, 4 minus 2 is 2. So now we have this. The manipulation that I want to make now, I am going to take row 3, and the new row 3 is going to be the old row 3 divided by 2. So this gives me 1, 1, 0, 2, 0, 2, 1, 3, 0, 0, 1, 1. And now I am going to subtract one lot of R3 from R2. So row 2, the new row 2, will be the old row 2 minus row 3. I'm doing this in a lot of steps because I don't want to mess it up. It's better to do this slowly and carefully than to rush it and completely mess it up. So now we have 0, 2, 0, 3 minus 1 is 2. So 0, 0, 1, 1. Now the new row 2 is going to become the old row 2 divided by 2. So now we have a new matrix, 1, 1, 0, 2, 0, 1, 0, 1, 0, 0, 1, 1. And the last thing we need to do is we need to make the new R1 the old R1 minus R2. And this will give us our final matrix, which is 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1. So this Gauss-Jordan reduction tells us that A equals 1. No, these should be capitals. This tells us that capital A is equal to 1, capital B is equal to 1, and capital C is equal to 1. So this is what we needed. This is what we were trying to find by plugging in the initial conditions. The initial conditions were helping us find the A, B, and C values from the general solution. So A is 1, B is 1, C is 1. So that means our solution, our specific solution, spec, is going to be y of x is equal to e to the minus x plus e to the x plus x times e to the x. Now this is this answer with a equal to 1, b equal to 1, and c equal to 1. We found a, b, and c were all equal to 1 by plugging in these values, turning it into a matrix, Gauss-Jordan reducing it, and then plugging them in. So this is now our specific solution. Now, as we have done consistently with these questions, we have to check them. So we have to take this, we have to differentiate it once, differentiate it twice, differentiate it thrice, plug all of those derivatives in to the differential equation that we started with, show that that all equals 0, and this will confirm that these are in fact solutions. These are some of the possible solutions. So we're going to do y prime of x is equal to minus e to the x plus e to the x. X times e to the x becomes, if we do the product rule, x derivative is 1 times e to the x, that's e to the x. E to the x derivative is e to the x plus x e to the x. So we could simplify this as minus e to the x plus 2 e to the x plus x times e to the x. second derivative, so this is our first derivative, second derivative, y double prime of x, negative e to the negative x becomes e to the negative x, 2e to the x becomes 2e to the x, the x e to the x again generates a new e to the x, so this actually becomes 3, then we have plus x e to the x, and then our third derivative, y dash 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 of x, e to the negative x becomes negative e to the negative x, plus 3e to the x stays as 3e to the x, the x times e to the x generates another e to the x, this becomes 4e to the x, plus x e to the x. So we have function, first derivative, second derivative, third derivative. Now we've got to plug them all in to the initial equation, this equation over here, and show that this is equal to 0 when the function and its derivatives are equal to these. So we get, this is our check, right? We're checking that this answer is correct. We're going to get y dash 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 minus y dash dash minus y dash plus y is equal to 0. This implies minus e to the minus x plus 4e to the x plus x e to the x minus e to the minus x plus 3e to the x plus x e to the x minus e to the x. Now we'll be very careful, this is minus e to the minus x, there should be a minus here. Minus e to the minus x plus 2e to the x. If you lose or gain a sign here, it's going to ruin everything. So we've got to be very, very careful. Plus x e to the x plus the function e to the minus x plus e to the x plus x times e to the x is apparently all equal to 0. So we just need to expand all of these brackets, simplify this, and then we're done. So we've got, let's see if we can cancel anything as we're going along. We could just expand all the terms actually, that might be a little easier. We have minus e to the minus x plus 4e to the x plus x e to the x minus e to the minus x minus 3e to the x minus x e to the x plus e to the minus x minus 2e to the x minus x e to the x plus e to the minus x plus e to the x plus x times e to the x is all equal to 0. We just need to find things, cancel them. So we have a plus x e to the x and a minus x e to the x. We have another plus x e to the x and another minus x e to the x. So that's good. 4 terms gone already. We have a minus e to the minus x and a plus e to the minus x. Minus e to the minus x and a plus e to the minus x. We've got 4e to the x minus 3e to the x. That's 1e to the x. Minus 2e to the x, that's minus 1e to the x plus 1e to the x, that's 0. So these all cancel each other out. This gives us 0 is equal to 0. This is what we wanted. This is true. And this means our check is both completed and successful. And it confirms that the specific solution that we found over here is in fact a correct solution to this third order ordinary differential equation.